Let's start with a zero-dimensional object, and that looks like this. It's just a dot or a point or a vertex. We'll call it a vertex. So n is 0, that's the dimension of our object. And let's look inside this object. What do we see inside? Well, not much. There's one vertex, and the vertex itself is zero-dimensional. So actually, I'll give another symbol for this. I'll say k is 0. So what we have on the outside, we have like the object itself. And then on the inside of the object, we have these geometrical elements that, okay, we'll see. In the next example, maybe is a little bit better because it has more detail. Dimension 1. So we take this object, we'll generate a dimension 1 object. We'll take this vertex and we move it like that, and we stop here. Now we have a compound object. We have a one-dimensional object. It's two vertices and an edge. You see? So, okay, so two vertices. Okay, and these are zero-dimensional. Okay, so I'll use k here. I'll say k is 0. That means the geometrical element making up our object is zero-dimensional, dimension k. And how many edges do we have? We have one edge like this. So k is 1 for the edge. And we can call these things components, like geometrical components or elements, what it's made of. Components is a nice word. Maybe I'll use components. Okay, so now we take this object and we move it in the, in some direction like this, stretch it out, and we have, look at this, we have a square, we have a square. And let's look at the components of this. This is now a two-dimensional object. It has a face now, not just vertices and edges. So how many vertices? We have 4 vertices. These are the k is 0, zero-dimensional components. And we have 4 edges. And these are k is one-dimensional component. And we have a two-dimensional component. The whole thing itself is one face. We have one face, and that's a 2D component. K is 2, like this. Okay. Now let's keep going. Let's make a 3D object. So we'll take our 2D face here, and we'll push it upwards like this. Let's see if I can draw this. Okay. Push it upwards and out like that. Okay, that's not so bad. Okay, so I took my face here. Let's color the face. And I pushed it upwards in this direction. And that's what I got. So now I have a 3D object. Great. And let's count the components, the geometrical components. How many vertices? 4 and 4, so that's 8 vertices. These are the k is 0. N is 3, k is 0. Okay, how many edges? We have 12 edges if you count them. Edges of a cube, it's 12. K is 1. How many faces do we have? 1, 2, 3, 4 around, and then top and bottom, that's 6. So 6 faces. So k is 2. That's the 2D component. But you have one 3D component, the cube itself. One cube, that's a 3D component. K is 3. That's very interesting. And so I'd like to make a notation that covers all of these components and counts them. So I'm going to invent this notation, nk. So here we have the dimension of the object. And here's the dimension of component. So for the case of the cube, I can write all these things down, all right? So cube is 3, dimension is 3, and how many vertices? Well, vertices are the 0-dimensional components, and there's 8 of these. Great. And cube, how many edges? There's 12 edges. Cube, how many faces? That's 2D. Faces are 2D. So that's 6 faces. And finally, for the cube, how many cubes in a cube? Well, there's 1 cube in a cube. So we have this very pretty notation which unifies our ideas about components and counting the components. So this notation is the basis of everything that we're going to be doing next. Now, notice that I was able to construct the object, the nth dimensional object. I was able to construct it from the n-1 dimensional object. You see, from the n is 2-dimensional square, I was able to construct the n is 3 one just by taking the square and kind of moving it and connecting the vertices. And so this gives us an idea that there should be what? Well, there should be a recursion relationship for the count of the components nk, because I'm just creating all the components by a recursive process here, by this type of recursive process. It just kind of remains for us to discover, well, what is this recursive process? Well, before we get into that, let's settle to a few things. So 0, 0, we'll define that to be 1. And in this case, anything with a negative dimension for a component, that's going to be 0 because we don't have those. There are no components with negative dimension. And also anything like this, where the component is larger, the dimension of the component is larger than the dimension of the object, that's also impossible, so there's 0 of those. We'll see that here. For example, how many cubes in this square? Well, 0. And, how many objects of dimension -1 in this square? Well, there's 0 of those. Okay, so we need to settle these things. We need to start somewhere, so we need 0, 0 is 1. So for the case of n is 0, the single vertex, all we have here is 0, 0 is 1. And in the next case, dimension 1, we have 2 vertices and an edge. Let's see if we can relate this to what we did previously here. Okay, so we're going to try to construct values for the count of all the components by looking at the previous thing. So let's count the vertices. So here we have dimension 1, and we're counting the vertices, so that's 1, 0. And how many vertices are there? There's 2. There's 2 times actually what came before. So I created it by taking this vertex and then moving it along and making another vertex here, you see? Okay, so I created it by doing 2 times 0, 1. So I can actually write this in a better organized way. Let's do it like this. 2, 0, 0. You'll see why soon. Okay, so I'm leaving a space so you'll see what's going on shortly. All right, now for n is 2, we have the square. All right, so I have created this square from that object here, the edge with the 2 vertices, and let's start computing. So here for 2, how many vertices now? Well, we have to think about that. It is 2 times the vertices that were in the previous picture. But the previous picture, the number of vertices is 1, 0, you see? Okay. And now, how about how many edges in here? Well, it's it's 2 times the number of edges in the previous one. Okay, 2 times the number of edges in the previous one, but also we have 1 edge for every vertex. You see, there was 1 new edge for every vertex we had in the previous one. So we add the number of vertices in the previous case. All right, so that's a very, very nice. Okay, so I'm going to quickly draw this cube, and let's count the components. All right, that's 3, n is 3. This is a 3D object, and the vertices, let's figure that out. Well, I've got 2 times the vertices of the previous one. You see, I have 4 on the upper face and 4 on the lower face, so that's 2 times 2 times 2, 0, yeah. Okay, and now for the edges. Well, I've got 2 times the edges, yeah, of the previous one, but I also have 1 edge for every one of these vertices. I have 1 edge here. There's 1 edge produced, so I'll color it in kind of brownish red, you see? So that's this stuff here. So I need the vertices, the number of vertices, yeah, like that. Okay. It's this challenge to figure this out. Okay, now the faces. Well, we have 2 times the number of faces. Okay, 2 times the number. We have a face here and a face here. So let me color that. That's blue and blue. That's 2 times the previous face. So 2, 1. Okay. But, sorry, 2, 2. 2, 2, yeah. Because face has dimension 2. And for each edge, let me color for 1 edge here, I got 1 face here, you see? So for each of these edges, I'm going to have another face. So I have to add all the edges of the previous construction in dimension 2. So there's dimension 2 and edges are dimension 1. Okay. And finally, let's see what we got here. 3, 3. Let's see if I can do this correctly. 3, 3. Well, that's going to be just 1 cube. That's the same as the number of faces in the previous dimensional object. Okay, very good. We have all of this. And now, if we reason about this very, very carefully, we end up with the following formula. nk, watch this. Okay, nk equals n minus 1, k minus 1, plus 2 times n minus 1 k. Let's see this in action. Okay, so let's finish. I'll take another color and let's finish this. So this is going to be through, this is n minus 1, 2, and 3, but that's 0. Okay, so this is correct, this formula. Now let's fill this in here. 3, 0, so this is going to be 2 minus 1, but this is 0. 0, okay, 0. And same here. If we try to fill this in here, okay, 2, 0, we're going to get a minus 1 here. Okay, this is going to be 1 minus 1, and that's 0, and so on. Okay, this is going to be 0 also. So this works perfectly as long as we keep in mind that anything, let's call it j minus 1 is 0, and anything with j plus 1 is also 0, which are not unreasonable things to say. And I'll show you this is actually related binomial coefficients in a minute, and you'll see that it borrows the behavior from binomial coefficients. So we have this absolutely beautiful formula. This is a recursion relationship. This is a spectacular formula. And I will look at how to put it in action now. Let's arrange these component symbols in something like Pascal's triangle. So we'll start with 0, 0, and then this is n is 1, n is 0 row. Okay, let me try to do it more neatly. Wait, 1, 0, 1, 1. Okay, so this is row n is 0. This is row n is 1. This is the dimension. The row will be the dimension. This is 2, 0. Then in the middle here, 2, 1, then 2, 2. And that's the maximum. You see, beyond the Pascal type triangle, this should be 0. So 2, 3 is going to be 0, yes? And we can keep going. So 3, 0, 3, 1, 3, 2, 3, 3. Okay, so that's n is 2 and n is 3. Now we can form, by using this rule, we can form any new one by taking the previous row. So suppose I want to find this one. Well, I take this plus 2 times this. The previous row, previous element, plus 2 times previous row, next element. So I take these two like this. That's the meaning of this recursion. So it's the element of the next row is defined from 2 previous elements of the previous row. You see? So I add these two together, and here I get 3, 1 plus 2, 3, 2. Okay, so I can in fact fill in an entire sort of Pascal-like triangle. So I start with 1, that's 0 dimension, 0, 0, and then 1, 1. Okay, so I add, to get this one here, I add this, which is 0, because it's beyond, this is a minus 1. This is 0 minus 1 element here. That's a 0. And the one after it, that's also 0. 0 plus 1, 0 plus 1 gives me a 2, so I should have a 2 here. And then 1 plus 2 times 0, that's 1. Okay, so I'm building up this triangle. So here there's going to be a 0. This is 0, and there's a 0 here. So 0 plus 2 times 2. Okay, again, let's write this rule down here. Okay, the one I'm calculating is the previous one plus the previous one on the left plus 2 times previous one on the right. Okay, let's see. Okay, so 0 plus 2 times 2. Don't forget that 2. That's what makes it different from Pascal's triangle. That's 4. Then 2 plus 2 times 1, that's 4. 1 plus 2 times 0, that's 1. So 4, 4, 1. So, okay, I can keep going now. So this is going to be 2 times 4 is 8. 4 plus, that's 12. So 8 vertices, 12 faces, 12 edges, sorry. And 4 plus 2 times 1, that's 6 faces. And then one cube. So this is n is 0, n is 1, n is 2, n is 3. Now we can then do this for the 4th dimension. So this is the hypercube, or the 4-dimensional hypercube. All cubes which are higher dimension than 3, we can call them hypercubes. So now we can figure it out by using this recursion. We can figure out what it's supposed to be. All right, so this is 0 here and 0 here. So let's compute. So 0 plus 2 times 8 is 16. I use this rule. 8 plus 2 times 12, that's 32. 12 plus 2 times 6, that's 24. 6 plus 2 times 1 is 8. And then 1 plus 2 times 0, well, that's 1. So in the hypercube, so we have the 4D hypercube. All right, we should have 16 vertices, 32 edges, 24 faces, 8 cubes should live inside the hypercube, and of course 1 hypercube. How do you draw a hypercube? Well, it's not that hard. You start with the cube and then you stretch it out the same way like we did. Let's see if I can draw that. Yeah, that's good enough. So I start with this blue cube, then I draw a red cube and I connect the corresponding vertices, and there, that's my 4D hypercube. Count the dots. How many vertices do we have? We have 8 plus 8. We have 16, which is correct. And the faces, well, you can count the faces. So, okay, I'm going to show you something called the tesseract, which is a stylistically nicer drawing of a 4D hypercube. Hang on a second. There it is. Right. Okay, so for now, you have to believe me that this object here, this one that we drew, the 2 cubes, and this one here, they are the same. And in the future video, I will show you why. I will prove it, actually, that they are the same. All right. So let's start by counting the vertices. 1, 2, 3, 4, 5, 6, 7, 8. You get used to it quickly when you do it a few times. 9, 10, 11, 12, 13, 14, 15, 16. Yes, so V is 16. Now, what about the edges? Well, you can count all of these edges. You see all these squares? And if you count all of the edges, you will find that, yes, indeed, there are 32 edges. And what about faces? Well, this is what a face looks like, this. Okay. Now, there are, if you count these carefully, like this is a face, here's another face over here, you see? The top part here is a face, you see? So you count all these faces, and how many faces do you have? Well, there's 24 faces. And what about the cubes? Well, in order to convince you that there are 8 cubes in this figure, I'll get a fresh one. There are indeed 8 cubes. Okay, let me show you one of them. So this guy here, let me show you one. Let's outline 1 cube. Now you just have to stretch your imagination a little bit, and you see this is kind of a cubical object right here. You see, this is the, you can imagine that this is the upper face, and then this in the back here, that's the bottom face. This is the front, let's say, front, and here back. And if you count these, yeah, you're going to have cubes, you will have 8 of them. Okay, so in fact, you should count these things. Maybe if I can find some of these tesseract pictures, I'll put them together. Well, I could maybe put a link in the description box, and you can color them in. You print it out yourself, and as an exercise, you color all the faces, edges, vertices. It's very fun to do, in fact. Very, very fun. So that's verified. We know that this works now, and let's see if we can go further than this and try to develop a formula, okay, which is like the binomial number formula, because we see that they're very, very similar. So if we compare the binomial numbers, the binomial numbers have this fundamental recursion relationship. Okay, and our hypercube numbers have a very, very similar relationship. The only difference is this 2 here. So we should be able to express the hypercube numbers in terms of the binomial numbers. So let's just make the triangle, the binomial Pascal triangle, and we'll compare it to the hypercube triangle. And let's see, that's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 1, 4, 6, 4, 1. Yeah, okay. Now here we have 1, we have 2, 1, we have 4, and 4, 4, 1, and then we have 8, 12, 6, and then 1, and then the big one, the hypercube, 16, 32, 24, 8, 1. So what's the difference? Well, if I factor out 2, let's factor out 2's from this stuff. What do I have? I have 1, 2 power 0, and here 2 power 1 times 1, and here 2 power 0 times 1. Here 2 power 2 times 1, and there's a 2 here. So it's 2 power 1 times 1, 2 power 1 times 2, sorry, and then 2 power 0 times 1. So I'm multiplying the binomial numbers by powers of 2. Okay, let's keep going. 2 power 3 times 1, that gives me this 8 here. Then 2 power 2 times 3 times this 3 here, that gives me the 12. Okay, then 2 power, oh, look at this, 2 power 1 times 2 power 1 times 3. Yes, that gives me a 6. Boy, I got scared there for a second that this wasn't working, but it is working. 2 power 0 times 1, that gives me this, and 1 and 1. Okay, let's see, does it work for dimension 4? 2 power, okay, I have to move things around a bit, hang on. 2 power 4 times 1, that's 16. 2 power 3 times 4, what's 2 power 3 times 4? That's 8 times 4, that's 32, I got it. 2 power 2 times 6, that's 24, yes. 4 times 6 is 24. 2 times 4, that's 8, we got it. Finally, 2 times the 1, okay, 1 times 1, 2 power 0 times 1 is 1. Yes, we have it. Oh, very good. So if we now write in closed form, we look at these powers, okay, it's 2 power n minus k, where k is the position here k is 0, k is 1, k is 2. Okay, so I subtract off k. It gets smaller as you go along, as k gets larger going along a row, and then times binomial number nk. So we have this beautiful formula. We have all components. This is incredible. It's beautiful. All geometrical components of dimension n hypercube. As an example, I'll show you an example of this. Let me calculate the number of faces in 10-dimensional hypercube. All right, let's see. Okay, so that's 10-dimensional hypercube. Faces are 2-dimensional objects, and let's compute this. And I just happen to know what it is. It's 11,520. There's 11,520 520 faces in a 10-dimensional hypercube. Just for fun, let's find the number of cubes in an 11-dimensional hypercube. Let's see how that what that looks like. 11. Okay, a cube is a component that's 3-dimensional, so that's 11.3, and this is 42,240. Imagine coloring all those cubes. Well, that was very, very cool. I hope you like it, and of course, click like and subscribe. Support my work so that I can bring you more fascinating mathematics videos. This one was really cool, I think. And I will see you next time.